Okay, let's have a look at team challenge number 5. This one people found pretty tricky, but it's really just the same problem we've always been doing. We're just doing it in a different direction. So the first part asks you what the original pH was when you take 4.75 mils of 0.8 molar NaOH and add it to 111 mils of 111 millimolar buffer that has a pKa of 6.95. And we're given the final pH to be 8.2. So what we have to do here is figure out what our knowns are. We know that we've added a certain number of moles of OH, so let's calculate that. We have 0.00475 liters at 0.8 moles per liter of OH added, which is equal to 0.0038 moles of OH added to the solution to bring about that pH change. We also know that the final pH was 8.2, so let's figure out what the ratio for A- to HA is when the pH is 8.2. So we have the Henderson-Hasselbalch equation. Alright, and we have a pH of 8.2. Okay. J. And this gives us a ratio, once we solve the anti-log, ratio of A- to HA of 17.78. Alright. Okay. So at this point, we know the ratio of A- to HA. Let's figure out how many moles of each of these we would have in the solution at that time. So we have a total of 0.111 molar, 111 millimolar, and we have 0.111 liters. So we have a total here of 0.01232 moles. That is equal to A- plus HA moles. We also know that the ratio is given down here, and we can combine the two to solve for the moles of A- and HA. So we'll just do it the way we would normally do that. We'll say that if we say that A- is equal to 17.78 times HA, we will say that 18.78 times number, and now it's number of moles HA, is equal to this 0.01232. And that gives us a number of moles of HA of 0.000656, if I can read my handwriting, moles. And the rest is A-, and that is 0.011664 moles. This makes sense because we're quite a bit above the pKa here. So they should be mostly in the A-. Now basically what we have to do is a reverse ice table. So the way I thought of this was, if we have HA and A- and then OH, at the end, so you have start, change, and equilibrium here. We're going to end up with essentially 0 there. At the end of all this, we're in this position here where we have 0.011664 moles, this is all moles, and 0.000656 here. Now we added the 0.0038 at the beginning, and it got converted over. So essentially, in order to get from here to here, we added the 0.0038 moles here because we took off the H pluses from up here and made those into A minuses. So if you just work backwards in the math and say, okay, this minus this is equal to our starting A minus so I just worked back up the ice table rather than working down it, I get this. Okay? And then I can simply take these numbers, plug them into Henderson-Hasselbalch, A minus and HA, with this pKa, and I get a final pH, or the initial pH, I guess, was 7.2. Okay, so this second part of Team Challenge 5 is a little bit trickier, but if you thought through the problem, it really wasn't that bad. First of all, what are we given? We're given, we have a solution that's 111 millimolar of a weak acid with pK of 6.95 and a starting pH of 7.2 that you figured out in the first part. Then you've added 6.0 mils of 0.75 molar HCl to some volume that we don't know, and we get a final pH of 5.99. So I think we're going to start by figuring out everything we can from what we're given. This is the easiest bit to look at, right here, where we have 0.006 liters times 0.75 moles per liter of HCl, and this gives us a value of 0.0044 moles of H plus added. Okay? We can also go through Henderson-Hasselbalch to figure out what the concentrations of HA and A minus are at each of these pHs. So just to quickly go through that, we have pH of 5.99 equal to 6.95 plus the log of concentration A minus over HA. Okay, we solve for that and we end up with the ratio. Once we figured out the anti-log, the ratio is equal to 0.1096. Makes sense, we're about 1 unit below the pKa. Okay, this is the ratio. We can rearrange to say that A minus is equal to 0.1096 times the concentration of HA, and the sum of the two is 0.111 molar. So we can substitute in to say that 1.1096 times HA is equal to 0.111 molar. And we can get our two concentrations here. HA equal to 0.1000 and A minus concentration equal to 0.011 molar. We do the whole thing again at pH 7.2, our starting condition. I won't go through every step here. I think we know how to do that now. And we end up with concentrations here of HA, put dot dot dot, you do the math, is equal to 0.03996 molar, and A minus is equal to 0.07104 molar. Now comes the kind of part you have to actually think a little bit. I think there's a bunch of different ways you can do this, but this is the way I figured it out. I said, okay, what if you had a whole liter of the buffer? What would be the number, the change in the amount of H plus? So I would take the difference between, so the difference is what I'm looking for, the difference in H plus per liter. So that is equal to the absolute value of 0.03996 and 0.1000, which is equal to 0.06 essentially, if you have all your decimal places in there. You can do it both ways, and you should do it both ways. Subtract this, take this and subtract that, and take this and subtract that. You'll get the same value. So basically what that's saying is it's 0.000600 moles of H plus need to be added per liter. But we had 0.044 moles of H plus added. So all we have to do is say, well, moles H plus were added divided by the 0.0, what was that number again? 600 moles per liter gives us 0.07, I think my numbers came out to 73 liters, 73 mils. If you carry all your decimal places, you'll get 75 mils. So it's just a way of thinking through the problem that you can figure out the change per liter and then figure out how the change per a smaller volume. The whole point of these is not to be ridiculously mathematically arcane, but the idea is if you understand the problem really well, you can do it forwards or backwards or sides to side. So hopefully you get that.